Okay, guys, thank you for coming in. We just finished the section on FlexE, and now we're going to switch the gear to OTN. The two things actually link to each other, and at the end of this presentation, I'll give you an idea of how they are actually connected. First, I'll start with a piece of good news. Xilinx is honored to receive the Innovation Award from Lightwave for our introduction of the OTN IP subsystems. And all these IP subsystems are created by Xilinx by connecting all the IP blocks together. And plus, we have done a lot of extensive testings. And essentially all these subsystems are like ASSP products. And all these are 100 gig based subsystems. Customers can create these subsystems multiple times to create higher density OTN framers. If you look at some of the notes that I put on this slide, if we just take the example of the 100 gig transponder, that normally will take the 100 gig Ethernet and map that into an OTN container and go out as an OTU4. With the 60 nanometer FPGA, which is currently we're starting to sample right now, you can actually put you can actually support essentially 1 terabit of throughputs. And all this subsystem really help customers to have essentially a very fast time to market. And obviously with FPGA, its programmability, you can essentially have a higher density design, and plus you also can essentially upgrade your designs. Okay. So now let's take a look at the market trend. Okay, what is going on in the market today, and even just at the trade show here, what are the key technologies, and I'll comment on whether they are important to Xilinx or whether we are actually just monitoring them. So the first trend that we're seeing is there is essentially continued growth in terms of traffic. So there's essentially a lot of traffic from video and also from mobile, and essentially those are all data traffics that it's essentially going to either source from routers, and those traffic needs to be transported. And of course, there's also the rise of essentially cloud service. And I actually found this very interesting 2 pie charts from Microsoft. So I think before the rise of the cloud, I think a lot of our focus is on essentially carriers. Okay, but if you look at the bottom pie chart, this is like the optical network under the cloud. Right now, the cloud has a much larger shares of the volume. Okay. And of course, the third is there's a lot of consolidation going on, and I think specifically for Xilinx, in the semi space, I think we all know there's a lot of consolidations, even in the FPGA space as well as in the ASSP space, and I think all these are essentially opportunities for Xilinx, and this is our current view at the moment. And if you look at also, from emerging technology point of view, here are 3 standard activities that Xilinx are actively driving and participating. The first one is FlexE. I think the panel here already described what FlexE is, and we are actively driving the standard. And plus, there's a demo at Xilinx, and as Luca mentioned, there's also a demo at Cisco. I strongly encourage you to visit Xilinx as well as Cisco or any other places where FlexE is currently being discussed. And of course, there's in the IEEE, there's also a discussion of 200 gig and 400 gig Ethernet service. And in the OTN space, the OTUCn, I think there is a lot of content already in place, and today actually a big portion of this presentation is I want to make sure you're aware that Xilinx is actually currently demoing essentially a OTN C4 Muxponder. So that's essentially a 400 gig Muxponder with a 400 gig big pipe on the line side. So I already mentioned, there's essentially, here are the three major technology that Xilinx is following very, very closely. First one is FlexE, or multi-rate Ethernet, essentially. And then the second one is the OTUCn, or some people might hear the catchword of FlexO. Okay, so O stands for optics. And then the PAN4, PAN4 IOs. So I think a lot of 5 vendors have already demonstrated the capability of PAN4 IOs from a standalone PHY point of view. But at the trade show here, Xilinx is actually also demonstrating our PAN4 IO. And our plan is to integrate those PAN4 IOs into our next generation FPGAs. In the optics front, there's also a lot of new emerging technologies or enablers, such as linear TIA drivers, flexible modulation schemes from coherent DSPs, as well as silicon photonics. In those areas, we are actively monitoring, and we will be talking with folks about how we can partner to provide essentially a better solution. So now let's take a look at what are the problems that we are trying to solve here. This is a very broad market, and the requirements are also very, very broad. And we think the best way to solve this is essentially a leading edge FPGA. Obviously, it's programmable. And here we're also providing a very comprehensive I/O portfolios. Here you can see the B100G. So this is essentially a new piece of IP that we have made available today. Internally, we also have a very different interlocking IPs available. And here we're mentioning 25G, 50G, as well as 100G and 40G, 400G. All these are IPs available today from Xilinx. So by being able to marry the leading edge FPGA with the IP, this is essentially our way of trying to provide essentially a very flexible and scalable optical transport. So now I'm going to focus a little bit more on the FPGA, okay, and then we'll visit the IP piece one more time. So this is the 16 nanometer FPGA. We're actually demonstrating it here at the show as well. Moving from 20 nanometer to 16 nanometer, we actually offer pin-to-pin compatibility. So today, if you have a design that is in 20 nanometer, you can actually migrate to 16 nanometer, just by simply replacing the bond. Okay. So you might ask, what is the advantage of 16? Obviously, at a lower geometry, you can take advantage of a power reduction. But actually, in 16 nanometer, there are also some interesting technology that we have embedded. Okay, so for example, you might be used to deal with a very smaller memory. It's called block memory. But now, in 16 nanometer, you actually have essentially a larger memory block that you can work with. Okay, ultra RAM, and plus our so-called stackable technology. This is actually our 3rd generation. Okay, and moving from 28, 22 now to 16, a lot of essentially enhancements has been made, and for example, right now even on the I/O side, you can actually get double of the 25G IOs moving from 20 nanometer to 16 nanometer. just take the case of a biggest device you will get from Xilinx in 20. You will get 60 25G IOs and 60 10G IOs. In 16 nanometer, you actually get 120 25G IOs. And those IOs are essentially sitting on essentially a die, okay? And it's essentially sitting on a 3D stackable die, essentially. And of course, in the 16 nanometer, there are also hot IPs. For example, the 100G Ethernet MAC, okay, it's actually a hard piece of IP. And what that means is you no longer need to use the logic or the fabric, the programmable logic to implement essentially a 100G Ethernet MAC, okay? So that ultimately will save the power for similar functions, or you can essentially free up your logic resource for additional features, okay? So now let's take a look at the beyond 100 gig IP portfolio, okay? So on the left-hand side, this is the demo that we have at the Xilinx booth, okay? It's essentially a Muxponder with 4 100 gig as the client, and on the line side is a 400 gig big pipe, the OTUC4, but the design actually also support OTUC2, which means it's a 200 gig big pipe, or it can actually also support OTUC1, which means you can also create 4 100 gig pipe as well. Now, so what are we doing after that demo? Okay, so currently, what our plan is to essentially offer more flexibility on the clients, on what type of client that we support. As you can see here, the current demo, it's essentially a fixed Ethernet that we can support on the client side. So the idea is, we actually we are currently working on essentially a design that will support FlexE, for example, on the client side, okay, or multi-rate Ethernet on the client side. So this is how starting. The two things were tied together: the flexible Ethernet as well as the flexible and scalable OTU line rate will essentially connect to each other. So this is essentially a Fluxponder, okay? And then of course for switching applications, I think Luca from Cisco also mentioned about FlexE. One of the benefits is to essentially have lower Ethernet pipes, okay, that can get into essentially a transport gear, and that lower order, essentially smaller Ethernet pipes can be mapped into essentially an ODU flex, okay? And the ODU flex then will eventually get into the right OTUCn, and that will essentially enable essentially a switching of ODU flex clients, essentially. So we have plans to do the FlexE or Ethernet client card, as well as the ODUK/ODUCn line card. So both are for switching applications with essentially a fabric interface to connect to a switch, okay? And so that's about 12 months, from now to the next 12 months. That's currently what we will be working on for the next 12 months. And then 24 months out, actually, we will be essentially looking at a single chip 1 terabit solution, okay? So now we essentially have a single chip 400 gig fixed Ethernet, but 400 gig line side. For the next 12 months, okay, we'll add additional features with our 16 nanometer FPGA to support flexible clients. And then 24 months out, we will really scale it to 1 terabit. And here I'm talking about one silicon supporting 500 gig moving to a 1 terabit. So this is the demo that is available today. It's On the right-hand side, this is what I call clients. Okay, so it's 100 gig Ethernet or a client OTU4, a gray color OTU4. And then on the left-hand side, this is the OTUCn. Okay, so by doing register configuration, we can support OTU C4, C2, or C1. And like I mentioned before, this is all implemented in VU190. And inside this box, there's essentially one device supporting this Muxponder. Okay. And there are actually already a lot of IPs that get essentially implemented. Okay, if you look at even for OTU4, we actually support the so-called OTU4 PT21 Mux. So what that means is if there's an OTU4 client comes in, I can even demultiplex down to a lower ODUK, and then the lower ODUK can then even multiplex up to the OTUCn. So that's what this PT22 Mux means. Okay, and this is the a bit more detailed block diagram of the device. So we actually also have internal pattern, essentially traffic generator and checker available. So actually at the demo, we actually use our internal traffic generator and checker. And on the 400 gig side, it's actually a loopback, because right now today, there's really no coherent module that can actually support essentially a C4 interface at the moment. So right now, we're just looping back the line side. All right, so here's the last slide, and here are the key takeaways I want you guys to take away. So we believe FPGA is a good solution for OTN. We definitely see OTN proliferating to metro, and there's essentially a requirement for having higher density, and I think higher density, normally people might think, oh, it might not be ideal for FPGA, but I think if it's a higher density of a simple function, then it is actually a very ideal solution by using FPGAs. You can really get a very, very high density and capacity from a single piece of FPGA. And of course, the emerging technologies, being able to reprogram, being able to essentially reprogram for upgrade and for essentially to follow essentially a standardization process. So while you try to get a demo out to your carriers, you actually can reprogram to be standard compliance once this standard is fully in place. And I already mentioned in the previous slide, right now we are looking at a single piece of silicon support 500 gig, but 1 terabit is coming very soon. The I/O, it's very, very important for OTN applications. And today we have essentially field-proven 28 gig I/Os, backplane capable, and now with the PAN4 demo that we have today, that is again re-anchoring how important or how much focus that Xilinx has put into essentially I/O technologies. I would also claim that the PAN4 I/O that we are demoing today is also backplane capable, and actually we have a 40 dB channel in our demo, and I would encourage you to take a look at that. Last but not least, on top of the silicon, we also try to make sure we have a lot of IP available today, and plus we also have a lot of ecosystems that we're currently working with, and hopefully together we can give you guys a very good solution for whatever you need. All right, thank you.